All right, everybody, welcome to a lecture on chapter 8. Let's walk through that a little bit. And let's go ahead and play from our start here. So our next thing will be introduction of hypothesis testing. You want to understand the logic of hypothesis testing, state the hypothesis and locate critical regions, conduct a z-test to make a decision, define and differentiate type 1 and type 2 errors, understand effect size and compute Cohen's d, make directional hypotheses and conduct a one-tailed test. So some stuff you'll need, z-scores from chapter 5, the distribution of sample means chapter 7, expected value, standard error, probability, and sample means. Let me just stop this for just a second. Go back to our screen share here. I think that's working, maybe. Yes, there we go. Okay. So let's talk about that. So tools you'll need, z-scores chapter 5, distribution of sample means chapter 7, expected value, standard error, probability, and sample means. So the logic of hypothesis testing. Hypothesis testing is one of the most commonly used inferential procedures. Definition: a statistical method that uses sample data to evaluate a hypothesis about a population. So the logic of hypothesis testing: state a hypothesis about a population, describe the expected characteristics of the sample based on that hypothesis, obtain a random sample from the population, compare the obtained sample data with the prediction that was made from the hypothesis. If consistent, the hypothesis is reasonable. If there is a large discrepancy, the hypothesis is, of course, rejected. So this is figure 8.1, the basic research situation for hypothesis testing. A population parameter is known or assumed before the study. The purpose of the study is to determine whether the treatment has an effect on the population mean. Figure 8.2, from the point of view of the hypothesis test, the entire population receives the treatment and then a sample is selected from the treated population. In the actual research study, however, a sample is selected from the original population and the treatment is administered to the sample. From either perspective, the result is a treated sample that represents the treated population. The 4 steps of a hypothesis test: state the hypothesis, set the criteria for a decision, collect data and compute sample statistics, and then make a decision. And we're going to do a worksheet that'll walk through this, so just get a sense of the steps right now. First, you want to state the null hypothesis. The null hypothesis, or H subset 0, states that the treatment has no effect, there is no change, no difference or relationship. The independent variable or treatment has no effect on the dependent variable. The alternative hypothesis, or H subset 1, states there is a change, a difference, or a relationship for the general population. Set the criteria for the decision. Step 2. Distribution of sample means is divided into 2 sections: those that are likely to be obtained if the null hypothesis is true, those that are very unlikely to be obtained if the null hypothesis is true. The alpha level, or level of significance, is a probability value that is used to define the concept of very unlikely in a hypothesis test. Step 2, critical regions. We're going to use that Z normal table to figure this out. Critical regions consist of the extreme sample values that are very unlikely, as defined by the alpha level, to be obtained if the null hypothesis is true. Boundaries for the critical regions are determined by the probability set by the alpha level. If sample data fall in the critical region, the null hypothesis is rejected. Figure 8.3. The set of potential samples is divided into those that are likely to be obtained and those that are very unlikely to be obtained if the null hypothesis is true. And you can see with the chart here what we're talking about. This will be known as basically your cutoff region. If it's here or beyond, you're going to reject the null hypothesis. If it's inside any of this, you'll retain the null hypothesis. And we'll walk through that a little bit. This is figure 8.4, the critical region, very unlikely outcomes for alpha of 0.05. This is what I just was talking about, where you reject the null hypothesis or where you retain it. So learning check 1 and 2. A sports coach is investigating the impact of a new training method. In words, what would the null hypothesis say? The new training program produces different results from the existing one. The new training program produces results similar to the existing one. The new training program produces better results than the existing one, or there is no way to predict the results of the new training program. And the way we would say the null hypothesis, you want to pause me, think about it for a moment. You can certainly do that. If not, the answer is the null hypothesis would be stated as the following. The new training program produces results similar to the existing one. Decide if each of the following statements is true or false. True or false, if the alpha level is decreased, the size of the critical region decreases. True or false, the critical region defines unlikely values if the null hypothesis is true. True, the alpha is a proportion of the area in the critical regions. True, this is the definition of unlikely. Step 3, collect data and compute statistics. Data are always collected after the hypotheses are stated. Data are always collected after establishing the criteria for a decision. This sequence assures objectivity and honest objective evaluation of the data. Step 3, compute a sample statistic z-score to show the exact position of the sample. Z is equal to the mean minus basically the sample mean minus the population mean over the standard error. In other words, Z is the difference between the observed sample mean and the hypothesized population mean divided by the standard error of the mean. Lastly, you make a decision. The obtained z-score value is used to make a decision for 2 possible outcomes. The sample data are located in the critical region. Decision, reject the null hypothesis. The sample data are not located in the critical region. The data do not provide strong evidence that the null hypothesis is wrong. Decision, fail to reject the null hypothesis. The null hypothesis is either an analogy for hypothesis testing. The null hypothesis is either rejected or the researcher fails to reject the null hypothesis. The process of conducting a hypothesis test is very similar to a jury trial. A jury trial begins with the null hypothesis, not guilty, innocent until proven guilty. Police and the prosecutor gather evidence or data to test whether the accused really committed a crime. With sufficient evidence against the defendant, the jury rejects the null hypothesis innocence claim to conclude that the defendant is guilty. With insufficient evidence against the defendant, the jury fails to find the defendant guilty. For example, there is not enough evidence of a guilty verdict, but does not conclude that the defendant is innocent. A closer look at the z-score statistic. The z-score is like a ratio. The actual difference between the sample mean and the hypothesized population mean divided by the standard error mean, and that large M is your sample mean, that small Greek mu, second one, is your population mean. Thus, for example, a z-score of 3 means that the obtained difference is 3 times larger than would be expected if the treatment had no effect. Decide if each of the following statements is true or false. True or false. When the z-score is quite extreme, it shows that the null hypothesis is true. True or false. The decision to retain the null hypothesis means that you prove the treatment has no effect. False. An extreme z-score is in the critical region. This is very unlikely if the null hypothesis is true. False. Failing to reject the null hypothesis does not prove it's true. There is just enough evidence to reject the hypothesis. Uncertainty and errors in hypothesis testing. Hypothesis testing is an inferential process. It uses limited information from a sample to make a statistical decision, which is then used to make a general conclusion. Sample data are used to make the statistical decision, allow us to make an inference and draw a conclusion about a population. Of course, errors are possible. Type 1 errors. A researcher rejects the null hypothesis that is actually true. A researcher concludes that a treatment has an effect when it has none. The alpha level is the probability that a test will lead to a type 1 error. It determines the probability of obtaining sample data in the critical region, even though the null hypothesis is true. Type 2 errors. Researchers fail to reject a null hypothesis that is actually false, or a researcher has failed to detect a real treatment effect. The sample mean is not in the critical region, even though the treatment has an effect on the sample. Type 2 error probability is not easily identified. Here are possible, table 8.1, possible outcomes of a statistical decision. We'll just pause this for just a second. All right, so to continue on, this is what, actually, I'm going to stop the share because the share is being a little difficult. So this is what a type 1 and type 2 error look like in terms of what would actually happen. So this is that table, possible outcomes of a statistical decision. So a type 1 error or alpha, reject the null hypothesis, actual situation, no effect, or the decision is correct, actual situation exists, and the null hypothesis is false. Or fail to reject the null hypothesis, your decision was correct, or you should have, but it actually exists, that's type 2 error, which is beta. So this is figure 8.5, the locations of the critical region. Boundaries are 3 different levels of significance. Alpha is 0.05, 0.01, and 0.001. Decide if the following statements are true or false. True or false, a type 1 error is like convicting an innocent person in a jury trial. True or false, a type 2 error is like convicting a guilty person in a jury trial. True, innocence is the null hypothesis for a jury trial. Conviction is like rejecting the hypothesis. False, convicting a guilty person is not an error, but acquitting a guilty person would be like a type 2 error. So more about hypothesis tests. So to summarize, step 1, state the hypotheses and select the alpha level. Step 2, locate the critical region. Step 3, compute the test statistic or the z-score. Step 4, make a probability-based decision about the null hypothesis. So reporting the results of a statistical test. A result is significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. Conclusion, reject the null hypothesis. In APA format, report that you found a significant effect, report the value of the test statistic, report the probability value of your test statistic. Factors that influence hypothesis test. The size of the difference between the sample mean and the original population mean. Larger discrepancies equal larger z-scores. The variability of scores, more variability of scores equals a larger standard error. Number of scores in the sample larger n equals a smaller standard error. Random sampling, some assumptions for hypothesis test with z-scores. Random sampling, independent observations. The value of the standard deviation is unchanged by the treatment. Normal sampling distribution. The unit normal table can be used only if the distribution of sample means is normal. So learning check. A researcher uses a hypothesis test to evaluate. A researcher uses a hypothesis test to evaluate the null hypothesis mean is equal to 80. Which combination of factors is most likely to result in rejecting the null hypothesis? Is it A, mean is equal to, the standard deviation is equal to 5, and the sample is equal to 25, standard deviation is 5, and the sample is equal to 50, the standard deviation is 10, and the sample is equal to 25, or the standard deviation is 10, and the sample is equal to 50. A research learning check 4. A researcher uses a hypothesis test to evaluate the null hypothesis where the mean is equal to 80. Which combination of factors is most likely to result in rejecting the null hypothesis? It was answer B, standard deviation is 5, and sample is equal to 50. Decide if each of the following statements is true or false. True or false, an effect that exists is more likely to be detected if the n is large. True or false, an effect that exists is less likely to be detected if the mean is large. True, a larger sample produces a smaller standard error and a larger z. True, a larger standard deviation increases the standard error and produces a smaller z. Directional one-tailed hypothesis tests. The standard hypothesis testing procedure is called a two-tailed non-directional test because the critical region is divided between the two tails of the distribution. However, sometimes the researcher has a specific prediction about the direction of the treatment effect. When a specific direction of the treatment effect can be predicted, it can be incorporated into the hypotheses. In a directional one-tailed hypothesis test, the researcher specifies either an increase or a decrease in the population mean as a consequence of treatment. This is the critical region, for example, 8.3. Comparison of one-tailed versus two-tailed tests. A one-tailed test allows rejecting the null hypothesis when there is a relatively small difference in the specified direction. A two-tailed test requires a relatively large difference regardless of the direction. In general, two-tailed tests should be used unless there is strong justification for a directional prediction. Learning check 5. A researcher is predicting that a treatment will decrease scores. If this treatment is evaluated using a directional hypothesis test, then the critical region for the test would be entirely in the right-hand tail of the distribution, or would it be entirely in the left-hand tail of the distribution, or would it be divided equally between two tails of the distribution, or this cannot be identified without knowing the value of the alpha level. So pause me. Of course, our answer would be entirely in the left-hand tail of the distribution. Concerns about hypothesis testing measuring effect size. Although commonly used, some scientists are concerned about hypothesis testing. Focus of tests is on the data, not the hypothesis. Significant effects are not always substantial. The effect size measures the absolute magnitude of a treatment effect independent of the sample size. Cohen's d measures the effect size simply and directly in a standardized way. Cohen's d is equal to the mean difference over the standard deviation from the treatment minus no treatment over the standard deviation. The magnitude of the d evaluation effect size. If Cohen's d is 0.2, that's a small effect. If it's 0.5, it's a medium effect, and if it's 0.8 or larger, it would be a large effect. This is figure 8.7, the appearance of a 15-point treatment effect in two different situations. In part A, the standard deviation is 100, and the 15-point effect is relatively small. In part B, the standard deviation is 15, and the 15-point effect is relatively large. Cohen's d uses the standard deviation to help measure effect size. Learning check 6. Decide if each of the following statements is true or false. True or false. Increasing the sample size will also increase the effect size. True or false. Larger differences between the sample size and the population mean increase the effect size. False. Sample size does not affect Cohen's d. True. The mean difference is in the numerator of Cohen's d. Statistical power. The power of a statistical test is the probability that the test will correctly reject a false null hypothesis. It will detect a treatment effect if one exists. Power is equal to 1 minus beta, where beta is the probability of a type 2 error. Power usually is estimated before starting a study, requires several assumptions about factors that influence power. Calculating power. Step 1, sketch the distributions for the null and alternative hypotheses. Step 2, locate the critical regions and compute the sample mean critical. Step 3, compute the z-score for alternative distribution and find power. This is figure 8.8. This is a demonstration of measuring power for a hypothesis test. The distribution on the left is the distribution of the sample means that would be expected if the null hypothesis were true. For the null distribution, the expected value is that the mean is equal to 80. The critical region is defined for this distribution. The right-hand side shows the distribution of the sample means that would be obtained if there were an 8-point treatment effect with an expected value for the alternative distribution of 88. The shaded area on the right gives the power of the hypothesis test. Notice that if there were an 8-point effect, roughly 1/3 of the sample means would be in the critical region. So power and sample size. Increased power. As effect size increases, power also increases. Larger sample sizes produce greater power. Using a one-tailed directional test increases power relative to a two-tailed test. Decreased power. Reducing the alpha level, making the test more stringent, reduces power. Using a two-tailed non-directional test decreases power relative to a one-tailed test. This is figure 8.9. This is a demonstration of how a sample size affects power for a hypothesis test. The left-hand side shows the distribution of the sample means that would occur if the null hypothesis were true. The critical region is defined for this distribution. The right-hand side shows the distribution of sample means that would be obtained if there were an 8-point treatment effect. Notice that nearly all of the alternative distribution is shaded. Thus, increasing the sample size n equals 25 has increased the power to nearly 100% compared to nearly 36% for a sample of n equals 4 in figure 8.8. Figure 8.10, the null and alternative distributions for a 16-point effect with n equals 4 and alpha equals 0.05, two tails. Compared to example 8.6 and figure 8.8, a 16-point effect has a power of 89.25%, which is much larger than an 8-point effect, which has a power of 35.94%. Figure 8.11, the distribution for a power analysis when the researcher assumes the treatment will cause a 20-point decrease. The null distribution is on the right side and the alternative distribution is on the left. All right, learning check. The power of a statistical test is a probability of a null hypothesis. Is it the power of a statistical test is a probability of rejecting a true null hypothesis, or is it the power of a statistical test is a probability of supporting a true null hypothesis, or the power of a statistical test is a probability of rejecting a false null hypothesis, or the power of a statistical test is the probability of supporting a false null hypothesis? The answer is the power of a statistical test is a probability of rejecting a false null hypothesis. Decide if each of the following statements is true or false. True or false. Cohen's d is measured alone. A hypothesis test does not measure the size of the treatment effect. True or false. Lowering the alpha level from 0.05 to 0.01 will increase the power of the statistical test. True. Differences might be significant but not of substantial size. False. It is less likely that the null hypothesis will be rejected with a small alpha. So if you have any questions, equations, concepts, do feel free to reach out. All right, let's walk through a few more things. All right, here we go, everybody. So this is one of the worksheets you can absolutely find that's due in right space here. So non-directional tests. A null hypothesis is not equal to the X or value or the null hypothesis. Alternative hypothesis is not equal to the X or the null hypothesis. A common measure of intelligence is S, specific technical information, and G, intelligence, general intelligence. We will assume that specific intelligence is measured on a scale from 1 to 70, and that general intelligence is measured on a scale from 1 to 90. Suppose we select a sample of college students to identify the specific or general intelligence of college students is significantly different than high school students. In the college student population, the scores are normally distributed in general intelligence of 65 plus or minus 17. That's our mean plus or minus our standard deviation. In the college student population, the scores are normally distributed in specific intelligence of 32 plus or minus 20. Compute the one sample Z statistic for both the general intelligence and the specific intelligence of this population to decide whether to retain or reject the null hypothesis at a 0.05 level of significance or alpha. In this sample mean of high school students, we record a sample mean of general intelligence equal to 70, M is equal to 70. We record a sample mean of specific intelligence of 54. The 4 steps are state the hypothesis, set the criteria for the decision, compute the test statistic, and make a decision. So some notes on hypotheses. The null hypothesis stated is a null statement about a population parameter such as the population mean that is assumed to be true. The null hypothesis is a starting point. You will test whether the value stated in the null hypothesis is likely to be true. An alternative hypothesis is a statement that directly contradicts the null hypothesis by stating that the actual value of a population parameter is less than, greater than, or not equal to the value stated in the null hypothesis. So let's walk through the first problem and you do the next one on your own. Let's determine if specific intelligence in college students is different than in high school students. First, we need to state the hypothesis. The null hypothesis, specific intelligence scores are equal to 32 in the population of college students. Alternative hypothesis, specific intelligence scores are not equal to 32 in the population of college students. Step 2, set the criteria for the decision. The level of significance is 0.05, which makes the alpha level 0.05. To locate the probability of obtaining the sample mean from a given population, we use the standard normal distribution. We locate the z-scores in a standard normal distribution that are the cutoffs or the critical values for the sample mean values with less than a 5% probability of occurrence in the value stated in the null hypothesis 32 is true. In a non-directional two-tailed hypothesis test, we divide the alpha value in half so that the equal proportion of the tail is placed in the upper and lower tail. In this example, the alpha is 0.05, so we split this probability in half. So a divided by 2 is 0.05 is equal to 0.05, divided by 2 is 0.250 for each tail. This is your rejection region. If you look at the table in the unit normal table, you get plus or minus 1.6. That has been posted in the unit normal table. This is where the cutoff, this is the cutoff value before the rejection region starts. But it is, if you are right at it, right dead on, it is you would still reject it. Therefore, the rejection region, the rejection region is the region beyond a critical value point in the hypothesis test. When the value of a test statistic is in the rejection region, we decide to reject the null hypothesis, otherwise we retain the null hypothesis. We looked at this earlier in the lecture. Next, you're going to want to compute this test statistic. Step 2 sets the stage for making a decision because a criterion have been set. The probability is less than 5% that we will obtain a sample mean that is at least 1.96 standard deviations above or below the value of the population mean stated in the null hypothesis. In this step, we will compute a test statistic to determine whether the sample mean we selected is beyond or within the critical values that we calculated in step 2. The test statistic for a one sample z-test is called the z-statistic. The z-statistic converts any sampling distribution into a standard normal distribution. The z-statistic is therefore a z-transformation. The solution of the formula gives the number of standard deviations for z-scores that a sample mean falls above or below the population mean as stated in the hypothesis. We can then compare the z-statistic called the obtained value to the critical values as we determined in the step 2. The z-statistic formula is the sample mean minus the population mean stated in the null hypothesis divided by the standard error of the mean. To calculate the z-statistic, first compute the standard error, which is the denominator for the z-statistic. So therefore, to do that, we calculate the standard error. We take 20 divided by the square root of 32, which is 3.54. And you want to be looking at the standard error of the mean formula in terms of how we got there. Then you compute the z-statistic by substituting the values of the sample mean. So 20 divided by the square root of 32. So that equals 3.54. Then compute the z-statistic by substituting the values of the sample mean. 54 minus 32 divided by 3.54 is equal to 6.24. Make a decision. To make a decision, we compare the obtained value to the critical values. We reject the null hypothesis. If the obtained value exceeds the critical value, it falls in the rejection region. So now do the same calculation. Don't worry about presenting your work to class, but if you follow the example that I gave you, you should be good to go. You're going to need the z-score and the standard error. The z formula and the standard error formula, which are posted in the master formulas. But in terms of what you're looking at, it looks something like this. All right, everybody. So let's just look at this on the whiteboard real quick. So what we're thinking about is the standard error of the mean, which is written like this, is equal to the standard deviation divided by the square root of n. And the other formula that you need is z is equal to x minus m over the standard deviation, which supports what I just did on the worksheet there a moment ago. So we're going to stop our share. We're going to go back to our document. And let's go back to our document. Okay, so that second one you can do on your own using the formulas that I just gave you. Some notes on directional versus non-directional tests. Non-directional or two-tailed tests are hypothesis tests in which the alternative hypothesis is stated as not equal to a value stated in the null hypothesis. Hence, the researcher is interested in any alternative to the null hypothesis. Directional tests are used one-tailed. Those are hypothesis tests in which the alternative hypothesis is stated as greater than or less than a value stated in the null hypothesis. Hence, the researcher is interested in a specific alternative to the null hypothesis. Part 2, directional tests. Suppose a researcher were interested in looking at improving test scores among elementary students where English is a second language by offering math immersion classes in the native language of the student. In this example, the immersion courses in the language of the student could improve math scores. For this reason, an improvement being greater than, the elementary school children would see an improvement. Suppose elementary school children in the general population show math scores of 50 plus or minus 5 points on a given math test. If we select a sample of 30 elementary school children in the math immersion classes and record a sample mean improvement of 60, m equals 60 points, then compute the one sample z-test at a 0.05 significance level of significance to determine if the math immersion program was effective. Step 1, state the hypothesis. The population mean is 50 and we are testing whether the alternative is greater than this value. Null hypothesis. With the math immersion program, the mean improvement is at most 50 points in the population. Alternative hypothesis. With the math immersion program, mean improvement is greater than 50 points in the population. Notice a key change for one-tailed tests. The null hypothesis encompasses outcomes in all directions that are opposite the alternative hypothesis. In other words, the directional statement is incorporated into the statement of both hypotheses. Therefore, in this example, the math immersion program in the speaker's native language is intended to improve math scores. Therefore, a one-tailed test is used because there is a specific expected effect. Step 2, set the criteria for a decision. The level of significance is 0.05, which makes the alpha level 0.05. To determine the critical value for the upper tail critical test, we locate the probability of 0.0500 toward column C in the unit normal table, which I've posted for you. The z-score associated with this probability is between 1.64 and 1.65. Therefore, the average of the two z-scores is 1.645, which is the critical value of the cutoff region. You should be able to sketch and gray out your cutoff rejection region. What we are talking about here in terms of what that might look like would be something like this. Let's go ahead and erase this. Let's erase this. And what I mean when I say cutoff regions, everybody, is here's your bell curve. These right here are your cutoff regions for a two-tailed test. It's for a one-tailed test, it's done a little bit differently. A one-tailed test looks kind of like this. You have your rejection region, and then since it's right here, and then your grayed out region. So this is your two-tailed test. This is your grayed out region. Your alpha would be, say, 0.05. That's the idea. So we're talking about this rejection region. If we have this improvement, or if we're not sure, and we're doing half and half, that's the rejection region. Let's go back to our document here. So step 3, compute the statistics. Step 2 sets the stage for making a decision because a criterion is set. The probability is less than 5% that we will not obtain a sample mean that is not at least 1.645 standard deviations above the value of the population mean stated in the null hypothesis. In this step, we compute a test statistic to determine whether or not the sample mean we selected is beyond the critical value we calculated in step 2. To calculate the z statistic, First, compute the standard error, which is the denominator of the Z statistic. So that formula, by the way, just so you know, let's go ahead and just write that out on our whiteboard here. That is going to be this formula right here. Let's erase again, eraser. That formula looks like this. The standard error is equal to the standard deviation over the square root of n, okay? Let's go back to our document here. Okay. So therefore, to first compute the standard error, you'll take 5 divided by the square root of 30, which equals 0.91. Then compute the Z statistic by substituting the values of the sample mean 60, population mean calculated by the null hypothesis. 50 in the standard error we just calculated. You want to use the formula that looks like this. This is our Z obtained value. Let's talk about our Z obtained value. Our Z obtained value looks something like this. Z obtained value, this is measuring it against the critical value, everybody, is equal to the mean minus the sample mean minus the population mean over the standard error, which we already have. And that's going to be our Z obtained value. Then we're going to compare notes and see what we have. So let's go back to our screen share. So again, we take 60 minus 50 divided by 0.91, we get 5.05. Because 5.05 is greater than the critical value, we know that the scores for the math immersion program in the native language improve the scores. The decision is to reject the null hypothesis. Because the idea is that if we go back to our whiteboard here, what's happened is the obtained value. So we talked about our cutoff regions. What had happened is the obtained value was over here in the gray area, and it was not at the critical. This is your critical value right here. Our obtained value was further to the right. That's how we know to reject our null hypothesis. This is our obtained value, or OBT, down here, past that point. So now that's how you would draw that in terms of drawing when it says draw figure 8.7. Now, moving on to our next thing, calculate this scenario on your own. Suppose elementary school children in the general population show math scores of 55 plus or minus 7 points on a given math test. If we select a sample of 30 elementary school children in the math immersion score classes, record a sample mean of m equals 64 points, then compute the one sample Z test at a 0.05 significance level to determine if the math immersion program was effective, and then create your own directional test. Stop our share. All right, so let's walk through effect and power size, guys. So here we go. Here's some scenarios. Let's walk through this. This is absolutely a worksheet you can find in Brightspace here. So 2 researchers make a test concerning the effectiveness of a drug use treatment. Researcher A determines that the effect size in the population of males is D is equal to 0.36. Researcher B determines the effect size in the population of females is D equals 0.20. All the other things being equal, which researcher has more power to detect an effect? So researcher A has more power to detect an effect because this researcher is making a test concerning a population with a larger effect size. Number 2, 2 researchers make a test concerning the levels of marital satisfaction among military families. Researcher A collects a sample of 22 married couples, n equals 22. Researcher B collects a sample of 40 married couples, n equals 40. All other things being equal, which researcher has more power to detect an effect? Researcher B has more power to detect an effect because this researcher collected a larger sample size. Number 3, 2 researchers make a test concerning standardized exam performance among senior high school students in one of 2 local communities. Researcher A tests performance from the population in the northern community in the northern community where standard deviation of the test scores is 110. Researcher B, test performance of the population in the southern community where the standard deviation of test scores is 60. All other things being equal, which researcher has more power to detect an effect? Explain. Well, researcher B has more power to detect an effect because the population from which this researcher is sampling has a smaller standard deviation. Number 4, explain how your answer to question 3 is related to standard error. Hint, you need to refer to the formula for computing standard error in order to answer this question. So the way you can answer that question is the population standard deviation is the numerator for standard error. The smaller the population standard deviation, the smaller the standard error, and therefore the greater the power. Hence, a smaller standard error will also increase power. Number 5, 2 researchers make a test concerning the same hypothesis. Researcher A tests her hypothesis at a 0.05 level of significance. Researcher B tests his hypothesis at a 0.01 level of significance. All other things being equal, which researcher has more power to detect an effect? Explain. Well, in this scenario, researcher A has more power to detect an effect because this researcher is making a test at a higher level of significance. The next one, 2 researchers make a test concerning the effects of music on mood. Researcher A tests the effects of music on mood and determines the likelihood of committing a type 2 error is beta is equal to 0.20. Researcher B tests the effects of classical music on mood and determines the likelihood of committing the type 2 error is 0.40. All other things being equal, which researcher has more power to detect an effect? Researcher A has more power to detect an effect because this researcher has a smaller probability of failing to detect a true effect type 2 error. So we're not going to do the group things. In fact, I think we're just going to completely eliminate that part of the assignment right now. So I hope everybody is watching these because I'm going to absolutely just make you have less homework right now. I'm just going to take all this right in front of you guys and just delete the homework section for you. I'm still going to leave the definitions. We're still going to review those, but I'm not going to give you extra stuff to do here because I feel like we literally talked about that in a pretty good sense. So yeah, we actually talked about all of this. So rather than tell you the same information here, we'll just I think we also covered that too. So we'll just delete that. In fact, we'll just talk about this stuff. So, in fact, yeah, we're not going to do any of this because I feel like we've already walked through this, and I have some stuff that'll help us with Cohen's D anyways, sort of as we need it. So, all right. So, definition of a test statistic. A test statistic is a mathematical formula that identifies how far or how many standard deviations of the sample outcome is from the value stated in a null hypothesis. It allows researchers to determine the likelihood of obtaining sample outcomes if the null hypothesis were true. The value of the test statistic is used to make a decision regarding the null hypothesis. A p-value is the probability of obtaining a sample outcome given that the value stated in the null hypothesis is true. The p-value for obtaining the sample outcome is compared to the level of significance or criterion. Significance or statistical significance describes that a decision has been made concerning the value stated in the null hypothesis. When the null hypothesis is rejected, we reach significance. When the null hypothesis is retained, we fail to reach significance. So the next thing we're going to do is we're going to do just some practice with SPSS with that file that's posted, which is the Excel file. So stop share for just a second, do a little SPSS, and I will conclude the lecture in a moment. Actually, I think you guys might not be too upset about this. We're going to skip the SPSS stuff on this assignment at this point. I'll let you know if I decide that to be different. But because we haven't dealt with crosstabs yet in terms of this particular stats, I'm not going to make you do crosstabs because I feel like we could, well, maybe I can make you do crosstabs. Yeah, we'll do crosstabs. Just, I want you to get your feet wet, really. That's the whole point of that. So let me stop the share. All right, the last thing we're going to do is just a little bit of practice with SPSS. There's a Baltimore Cities Excel file that you should have been able to download that is absolutely in under the folders here. We're going to just say, we're going to import data, and we're going to import an Excel file. We want to read and write, of course. And then let's see, maybe downloads right here. So with SPSS, you got to be careful because what it does sometimes is you have to think through where what you're looking for probably is. See now, here we go. Baltimore City employees, we're going to import. This is like one of the coolest things ever, I think, importing a file into SPSS. So we're just going to do what I just did there. And we're going to just let it do its thing, give it a second. And we're just going to do something real basic. And this is not so much what we're looking for as an understanding of what you're doing at this point, because we have not addressed crosstabs. This is just an opportunity to practice and get familiar with SPSS. That's the point here. So it's going to get the data here, and we should have something. This is what you might be looking at. It's going to take a moment. And for sure, maybe it's in the window. And that should have imported. Let me see why that didn't import. Oh, it did import. It's just in a different file. Okay. Just a different window. Okay, here you go. So that was importing that file. And then all I want to do is just very, very easily, we're going to click on Analyze. And we're going to click on Descriptive Statistics. We're going to click on, we're going to go Analyze, Descriptive Statistics. And we're going to click on Crosstabs. And then we're going to put, let's say, job title. And we're going to, now let's compare the annual RT to the gross. And then we're going to click on statistics in the cell buttons. And as you can see, we can do a lot of this stuff here. The thing that we really want are the row percentages. We could be like, we didn't really address the ETA. Yeah, we can do correlations if we wanted to. Say continue, say okay. Oh, that's why I didn't like it. Okay. There's too many because the file's too big. So we'll do something different. Let's just say analyze, descriptive statistics. Let's just do frequencies. Let's say job title and hire date statistics, median mode sum, central tendencies, some quartiles, talked about that, percentiles, let's look at standard deviation, variance range, minimum, maximum, and standard error, because I feel like that's what we've been looking at sort of the most here. Standard error of the mean, continue, and say okay. Let it build the frequency table. Don't worry about crosstabs. We're not going to do that. We're just going to look at this, and it's going to do all the math for us. And then I just want you to go File, Save As, SPV file. That's fine. I can read SPV files, upload it. Also upload your save data file. So we would call it SPSS chapter 8 practice, for example. Okay. Just so I know what it is that you're doing, so I can check your work. And then you'd say save. And then you could also take and save as. So that was SPV. So that was like your results. I want you to do that. But also go back into the file and go File, Save As, and just show that you've been able to import the file. That's another good thing to know how to do. And then, save it as whatever that is. Well, you can just say, in this case, chapter 8, save, chapter 8, save, maybe practice. Literally that easy. Do both files. Now, if you want to be fancy, by the way, guys, this is pretty cool. You can go file, export, and you can make this into Excel if you wanted to. And as long as you know what path it is, it'll save that way. You can also do a CSV if you wanted to. And then the other thing that's cool is if you go back into like your SPV file, which you can always find with like going to the window here. That should be it right there. You can go file and you can export also right here. And then you have some options. You can make it like into a PDF file, and then just make sure you label it so you know what it is. Maybe like right here, as well as watch your path, guys, so you can find it for uploading purposes and say 8. And then we can say, okay, and now we're going to get a PDF file that SPSS is going to build, which I think is pretty awesome. You'll see a window like this. It'll take a little bit of time, not a lot of time, but also say if you're working with SPS in the future, being able to show it to your bosses, your managers, absolutely a pretty cool and important thing. So again, we're going to skip crosstabs. We're just going to do some descriptive statistics, including the standard error, the mean, in terms of stuff that we've been looking at in SPSS, and then just submit that along with this worksheet. Hopefully that information is helpful. We'll stop our share. Hope you learned something, and I will see you hopefully live, or we'll just keep recording videos. Please call me, text me, email if you have any questions along the way. And if you want a live chat, let me know. I'll get this posted. And I think I'll give you guys a little more time on the exam. I'll post an announcement to how much time momentarily. Have a wonderful day. Hope you enjoyed the lectures, and I will see you asynchronously. Hope you learned something. I'll see you in the next video.